So this was for n equals, so just for the video purposes, this is problem 3B from the test 4 review. And so I said, let's write out the first couple of terms. So this was for n equals 1, this is for n equals 2. And so now for n equals 3, I would have negative 2 to the 5th. So that would be negative 32 over 5 cubed, which is 125. So I look at this, and if I ask you to actually find the sum, there are very few series for which you can find the sum. One is if it fits one of the patterns, like in that table we just had at the end of the last set of lecture notes. There. Like, we could see if it fits this pattern. Well, there are no factorials in the denominator. It's just powers of 5 in the denominator. So it can't be anything with factorials. It's not 3, 5, 7. So it really doesn't necessarily look like any one of these. This one doesn't even have a denominator. But so if it doesn't fit the table, the other things we know to do are, if we can decompose it using partial fraction decomposition, but this denominator is just 5 to the n. There's not really a way to factor that. What's the other type of series? Geometric, right? And so we would ask if this series is geometric. So to get from the first term to the second term, what would I have multiplied by? Negative 2 over 5. And so if we multiply the second term by negative 2 over 5, do I get the third term? Yes. So this is a geometric series, and my ratio is negative 2/5. And as long as the absolute value of your ratio is less than 1, your series converges. And the absolute value of our ratio is less than 1. So the series converges, and the sum is k over 1 minus r, where k is the first term. So the first term is negative 8/5. 1 minus the ratio is negative 2/5. So we have negative 8/5. So this would be 1 plus 2/5. 5/5 plus 2/5 is 7/5. And then you can just invert and multiply. So times 5 over 7. So negative 8 over 7. What else? Number 7. Number 7. Okay, determine whether the series converges or diverges. And so when I ask this, I also expect you to justify your answer and to show work and to use a test properly. And so I give on the first page, we don't get a lot of formulas for this particular test because we're not going to really be doing much integrating. So I give you the tests, the names of the tests. So like when I was grading the extra credit, somebody said I use the comparison test. There is no comparison test. There's a direct comparison test and there's a limit comparison test. And they have two separate methods. And you have to show the steps of that test. So first let me write this down and then we'll decide which tests we're going to use. Okay, so the first thing you should always check is to see if the nth term goes to 0, because if it doesn't, you're done. It diverges. But if the nth term does go to 0, that doesn't, it could still converge or diverge. So definitely our nth term goes to 0 because the numerator is always 1 and the denominator is getting bigger. So then the question is, well, so let's look at those tests again. Some of them we can rule out right away. It's not a p-series. It's not 1 over n to the p. You could write out the first few terms, but you would see it's not geometric. You can't use partial fractions when things are under radicals. I don't want to integrate that. Alternating series is only when you have -1 to the n in there somehow. That doesn't. So it's either direct comparison, limit comparison, ratio, or root test. And you could try the ratio or root test, but you'll get 1 both times. So now we're looking at direct comparison. You might not necessarily just automatically know that looking at it, but think of, well, you could split this into 3 different cube roots, right? So you could think of it as the cube root of n, the cube root of n plus 100 times the cube root of n plus 1,000. And if you did each one of those separately, well, the nth root of the numerator is always going to be 1. And so if you think of taking the nth root of the cube root, well, first of all, you can write the cube root of n as n to the 1/3 power. And then when you take the nth root of n to the 1/3, I can think of that as n to the 1/3 to the 1 over n, but you can multiply in whatever order you want. So I can say that's n to the 1 over n to the 1/3. Right? Both of those would give you n to the 1 over 3n. And we know what happens to this. The nth root of n goes to 1, right? To the 1/3 power. So this is just going to be 1. All 3 of them are going to be 1. So the ratio test it's going to be inconclusive. And usually if the root test is inconclusive, so is the ratio test. So now we're into direct comparison or limit comparison. And limit comparison is generally the safer way to go because you don't have to prove one is always smaller or always bigger than another. Like the one on the group work was n squared plus 1 over n cubed plus 1. Well, you have to prove, if you want to compare it to using the direct comparison test, n squared over n cubed, you have to prove it's always smaller. And the thing is, leaving off the 1 in the numerator does make it smaller, but leaving off the 1 in the denominator makes it bigger. So there's no way to convince anyone saying, well, the first 2 or 3 terms, these are smaller than those, or bigger even. Doesn't help. You have to show it's always true. So here, I would think of doing the limit comparison test. And I would ask myself, so I'll call this my A sub n. And B sub n will be the one that I think it acts like. So when n is really, really big, what parts of this expression aren't going to matter? The 100 and 1,000. So if n is 5 billion, it doesn't really matter too much that you're adding 100 or even 1,000, right? So when n is really, really large, it's almost like the 100 and 1,000 have no effect. All that really matters are the n's. So it's almost like we just have n cubed under the radical. But if we have 1 over the cube root of n cubed, That's 1 over n, right? So I think this series is going to behave like this series. Now, why won't direct comparison work? This series is smaller than 1 over n. And so what does this series do? It diverges. It's the harmonic series. And since this series is smaller than that one, that doesn't help. Smaller than infinity could be finite, or it just might take longer to get to infinity. So that's where we do the limit comparison. And the limit comparison is we just do the ratio of the two. And it really doesn't matter which one you put in the numerator and which one you put in the denominator. It matters, what matters is the answer you get. So say, just a little refresher on limit comparison. So say we knew a sub n converges, and the limit as n goes to infinity of a sub n over b sub n is 5. So then, do we know what happens with b sub n? It converges, right? If what this is saying is for really large n, the b sub n's are basically just, or I'm sorry, the a sub n's are basically just 5 times the b sub n's. So their ratio is they're getting closer and closer to 5 over 1. So the a sub n's are like 5 times as big as the b sub n's. But if a sub n's add up to some finite number, then 5 times b sub n, they're going to add up to some finite number, right? The b sub n's are even smaller, right? Whenever you get a constant multiple, whenever you get a constant, that means eventually one is basically a constant multiple of the other, and you can just factor that constant multiple out. A constant times some finite number is a finite number. A constant times infinity is infinity. So if one diverges, they both diverge. If one converges, they both converge. What if, so same hypothesis, a sub n converges. So I should have said finite non-zero number in the first one. What if the limit is 0? Then which one is bigger, a sub n or b sub n? B sub n. B sub n, because the denominators must be getting huge compared to the numerator. So now what about b sub n? Does it converge, does it diverge, or don't we know? We don't know, right? It's bigger than a finite number, but it just might be some bigger finite number. But it might be infinity. So we don't know what it does. The third possibility is we could get infinity as our limit. And then we would ask ourselves, okay, does that help us? Can we determine the behavior of b sub n now? Well, which one is bigger if the limit is infinity? A sub n is bigger. Right, and if it's bigger and it's finite, then this one has to be finite. I should have absolute values on all of these. I'm assuming that we're leaving off, if there's the alternating sign part, I'm leaving off the -1 to the n part. Okay, so it would be really great if I got a finite number, because then I automatically know my answer. I don't have to go through this process, but it's fine. 0 and infinity, I just have to ask myself those 2 questions. So this one, we just want to be a little bit clever in how we write things so we don't have to keep using L'Hopital's over and over and over. So our a sub n, since they're both fractions, I'm going to, instead of dividing by b sub n, I'll multiply by the reciprocal, so it'd be n over 1. Well, I can multiply this into one fraction and I'd have n over the cube root of that. And we'd say, well, obviously the numerator is going to infinity and the denominator is going to infinity. And when we get that, we know we should use L'Hopital's, but think about taking the derivative of this. You'd have to use the chain rule, right? It's this to the 1/3 power, so you'd have 1/3 this to the negative 2/3 times the derivative of what's inside. So you're just going to get another cube root back. It's never going to go away. So I somehow want to avoid taking the derivative or applying L'Hopital's with that cube root. And it would be really nice if I could get everything under the cube root. And then since the cube root is a continuous function, then I could take the limit inside the cube root. So the denominator is fine. n plus 100, n plus 1,000. Now, if I want this to be under the cube root as well, it has to be n cubed. So now I can take the limit under the cube root, and now we have polynomials, which are easy to take derivatives of or apply L'Hopital's. Actually, let's think of just multiplying out. So first, if I distribute the n through, I'd get n squared plus 100. And then doing FOIL again, I'd get n cubed plus 1,000 n squared plus 100n plus 100,000. And actually, instead of using L'Hopital's, you could just divide every single term by n cubed. Right. So we just have 1 in the numerator and 1 plus 1,000 over n plus 100 over n squared plus 100,000 over n cubed. But all of these three terms in the denominator just go to 0. So I just have 1 over 1. So I have the cube root of 1, which is 1. So when n is really big, a sub n and b sub n are approximately equal. And since the series for b sub n diverges, then that means our series diverges. Another question? Mm-hmm.
The one in the group work.
Okay.
Number 3.
N squared plus 1, so the one I talked about?
Yeah.
Okay. So this was the 11-7 group work, the extra credit. Okay, so I just mentioned that trying to do the direct comparison is not the best way to go about it. Technically, I bet you could use the integral test for this, but integral tests remember, requires some work leading up to it. So just a little reminder, if we were to use the integral test, whatever the integral does, the series does. So if the integral converges, the series converges. But before we can even use the integral test, we have to show that f sub x, or not f sub x, f of x is positive, continuous, and decreasing. And usually the positive and continuous part is really easy. You can just say, I can just tell by looking at it that it's positive and that it's continuous. Maybe it has a denominator that's 0 at -2, but our series starts at 1, so we don't have to worry about it. So the positive and continuous part are really easy to show. Decreasing, if your numerator is not constant, how do we show something is decreasing? Do what? Well, but if the if the numerator is constant, then yeah, the denominator will just get bigger. But if the numerator has an x in it, the numerator gets bigger too. So you can't say that the function is getting smaller when both the numerator and denominator are getting bigger.
So you have to find a derivative.
Derivative, right? Show the derivative is what? Is negative. If this 1 weren't there, well, first of all, then that would make the direct comparison part pretty easy, because leaving off +1 in the denominator makes it bigger. But if this was like -8 or something and this started at 5, then leaving off the -8 wouldn't really help us so much. And if it were just n squared in the denominator, then making a u substitution would mean the integral would be relatively easy to evaluate. The f of x, when I talk about the f of x, it's just you replace all of the n's with x's. Okay, so this one, I don't want to do direct comparison because leaving off this one makes it smaller, but leaving off this one makes it bigger. So it's only if leaving off the constants does the same thing both times when you can use the direct comparison test. So in general, it's much safer to use the limit comparison test. So just like I did on the last one, you ask yourself what you think it acts like. So if I call this my a sub n, I think I'll compare it to b sub n equals what? 1 over n, because when n is really, really large, those plus ones aren't going to matter. And so it would be like n squared over n cubed, which is 1 over n. These two n's cancel 2 of those, and we're just left with that. And so then we do the limit as n goes to infinity. And this is the series we just looked at. That series, the series 1 over n diverges. It's the harmonic series. And so if I do a sub n over b sub n, and maybe I switch the numerator and denominator from the last one, but it doesn't really matter. I'll ask myself the questions I need to ask if I get 0 or infinity. So a sub n is n squared plus 1 over n cubed plus 1. Dividing by b sub n is the same as multiplying by its reciprocal, so times n over 1. So if I multiply out, I get n cubed plus n over n cubed plus 1. And then we can divide every term by n cubed. So I'd have 1 plus n over n cubed is 1 over n squared. 1 plus 1 over n cubed. Well, both of these go to 0. So we just get 1 again. Any non-zero constant means both series have the same behavior, either both diverge or both converge. And we compared it to one that diverges, so our series diverges. Okay, there's one that I think is on here that I want to do. Let's look at 12. So there are two different ways we could do problem 12. Actually, I guess I would think primarily of one way here. The binomial theorem, oops, that we just learned works when it's centered at 0. I say first for non-zero. I'm gonna flip up a second. I want to see what I have here. Okay. So finding the first 4 terms of the Taylor series. So this is the one where you have to remember the formulas for the C's. So C0 was just the function evaluated at wherever you're centering it. The one you did in group work and we did in class was centered at 0, so it was just f of 0, but here we're doing it at -1. C1 is the first derivative divided by 1 factorial. We want 4 terms. So C2 would be the second derivative divided by 2 factorial, and the third, C3, is the third derivative over 3 factorial. And so I think they call it I think I called it T3 on the Maple project, and I think WebAssign calls it T3 as well, or maybe T2, no, T3. So it would be C0 plus C1. Normally you multiply by powers of x, C0 x to the 0 plus C1 x to the 0. That's if you're centered at 0. It's x minus -1. So we would have x plus 1 to the first, and then plus C2 x plus 1 squared plus C3 x plus 1 cubed. So those are going to be the first 4 terms. So we have to find the constants, which involve finding the first, second, and third derivatives. So we can find C0 right away. So C0 is just f of -1, which is the square root of 3 plus -1 squared. So that would be the square root of 4, 2. So we already know the first term is 2. So now we have to find f prime. Well, I would think of this as 3 plus x squared to the 1/2 power and use the chain rule. So the 1/2 comes out in front. 3 plus x squared to the -1/2 times the derivative of what's inside, which is 2x. So the 2's cancel, and we get x over the square root of 3 plus x squared. So f prime of -1 is -1 over the square root of 4, or 2. So C1 is this divided by 1 factorial, which is still just negative 1/2. Okay, so we know our C0 and our C1. So for C2, we need the second derivative. So I think I'm just going to use the quotient rule on this. So it'd be the bottom times the derivative of the top, which is 1, minus the top times the derivative of the bottom. Well, we took the derivative of square root of 3 plus x squared, and this was our answer. X, right? F prime, our F was square root of 3 plus x squared. So the derivative of that was our F prime. So x over the square root of 3 plus x squared. All over the denominator squared, well, squaring the square root just gives us 3 plus x squared. If I asked you to find the first 4 terms, on the test, I would be more likely to only ask you for the first 3 instead of the first 4 if I'm going to ask you to take a derivative like this. Taking the derivative of this requires a little bit of algebra. I'll show it to you, but if I only asked you to find the first 3 terms, I would just say, let's just go ahead and plug in -1 right now. So we'd have the square root of 4, which is 2 times 1, minus -1 times -1 over the square root of 4. Over 4. So this is kind of ugly, but first of all, 3 negatives make a negative. And I'd have just 1/2 over 4. I'm just going to multiply top and bottom by 2. And think of distributing. 2 times 2 is 4. 2 times 1/2 is 1. So I'd have 4 minus 1, or 3/8. So C2 is f double prime over 2 factorial. So it's 3/8 over 2 factorial, which is just 3/8 over 2, or 3/16. Okay, one more term. And I'm going to actually, before I take the third derivative, I want to simplify the second derivative. So I have these square roots, 2 different square roots in the numerator. Times 1, I don't need that. So I'll just write square root of 3 plus x squared minus x squared over root 3 plus x squared over 3 plus x squared. And I'm going to multiply top and bottom by the square root of 3 plus x squared. So it's going to make the numerator look nicer. And the denominator, if we have it to the first power times the square root, I can just write that as 3 plus x squared to the 3/2. So now if I distribute 3 plus x, root 3 plus x squared times root 3 plus x squared, I just get 3 plus x squared. Minus, and then when I distribute it to the second term, the square roots cancel, and I have minus x squared. So the x squareds cancel. So I just get 3 over this, which actually does make the third derivative pretty easy to calculate. So we do the bottom times the derivative of the top, but the derivative of the top is 0. So minus the top times the derivative of the bottom. You could also write this as 3 times 3 plus x squared to the negative 3 halves and use the chain rule. That's probably the easier way to do it, but just since I used the quotient rule before, I'll use it again. So I'd have 3 halves, 3 plus x squared to the 1 half times the derivative of what's inside, which is 2x, all over the bottom squared. So I have it to the 3 halves power, and then I'm squaring it. Well, just multiplying exponents leaves this so that it's cubed. So the 2's cancel in the numerator, and so I'd have negative 9. I'd have an x. And let's simplify this one into this one. So there's a 1/2 in the numerator and 3 of them in the denominator. So this 1/2 will get rid of 1/2 of those. So 2.5 will be left. And so f triple prime of negative 1 would be positive 9 in the numerator over 4 to the 5 halves power. We'll think that's 4 to the 2.5. So you have 4 squared, which is 16, times 4 to the 1/2, which is 2, because 4 to the 1/2 is the same as the square root of 4. So you'd have 9 over 32. And so our C3 is the third derivative divided by 3 factorial. So that's 9 over 32 divided by 6, which is the same as multiplying by its reciprocal 1 over 6. And 3 goes into both of those. So 3 over 64. So now we know T3 is 2 minus 1/2 times x plus 1 plus 3/16 x plus 1 squared. Did I lose a minus? I wouldn't expect it to be plus minus plus plus. It's possible I have a sign error somewhere, but let me check.
You got a negative 9.
Yeah, I have a negative 9, but then I plugged in negative 9x, but I plugged in negative 1. So let me check. So we can do we're doing Taylor series for, this was the square root of 3 plus x squared centered at x equals negative 1. 2 minus 1/2, nope, plus 3/16 plus 3/64. So just worked out that way. All right. So I'll have the solutions to all of the rest of the group work. I think it's up right now through 11:8 maybe. So I'll get the 11:9 and both of the 11:10s up.